Okay, good day, everyone, and welcome. We're excited to have you join us for today's presentation on advanced softening technology for DLE eluate processing. I'm Louis Ponzani. I'm sales manager with CaCO₃, and I'm principally responsible for business development around, among other things, our lithium specific offerings. Thank you for taking the time to be here. This is our first webinar of the year, and we expect to have many more interesting topics to come. Before we get started, I just want to go over a few housekeeping notes. One, to reduce noise, all attendees are muted. If you have questions on today's topic, type it into the Q&A box, and we will answer questions at the end. For any technical difficulties, again, type it into the Q&A, and we'll help right away. Lastly, this webinar is being recorded and will be available post-webinar for viewing. And now I'll introduce our speaker, Mahdi Jazayeri. He is the Technology Development Lead here at CaCO₃. And Mahdi, over to you.
Okay, perfect. Thank you so much, Louis, for the introduction. All right. Hello, everyone, and thank you for joining us for today's webinar. I am Mahdi Jazayeri, Technology Development Lead here at CaCO₃. Today, I will walk through advanced softening technology for DLE eluate processing and how Recoflo softener helps deliver low hardness with minimal lithium loss. This is a technical topic, but I'll keep it simple. What's the problem? What's the solution? And what does it mean for operations and costs? Here's the outline for today. I will start with CaCO₃'s history. Then I'll do a brief ion exchange refresher. I'll cover our Recoflo technology in terms of operation and performance. Then I'll go into Recoflo softener, our advanced hardness removal solution for DLE. At the end of the presentation, we'll address your questions. Okay, let's look at CaCO₃ timeline and show how the platform developed and where we are today. Recoflo was originally developed at the University of Toronto in the mid-1960s, and CaCO₃ was founded in 1970 to further develop and commercialize the technology. A couple of key milestones include CaCO₃ patenting the overpacking design and installing the first acid purification unit for mixed acid in 1980s. Our water purification experience goes back to 1991 when we sold our first WDU. In 2019, CaCO₃ was acquired by Koch Industries and integrated into Koch Separation Solutions. We built our first DLE pilot unit in 2023, and later in 2023, Koch Separation Solutions transitioned to new ownership and became Covalis Separation Solutions. Our sustainable future focus areas are mainly on lithium eluate treatment, rare earth metals, and carbon capture. With this history, we have delivered more than 3,000 systems across 67 countries, and that total footprint reflects what we have doing at CaCO₃ for decades. Okay, let's have a quick look at where CaCO₃ sits within Covalis. Covalis brings multiple separation platforms under one group. We have Covalis Membrane Solutions, which provides integrated membrane solutions like RO, ultra, and nanofiltration technologies. We also have Relco, which provides evaporation, drying, cheese making, powder handling, and packaging technologies in food and dairy markets. And last but not least, CaCO₃, which I'm representing, is the ion exchange arm. CaCO₃'s ion exchange technology relies on proprietary Recoflo fine mesh resin. The resin bead is designed to operate with a smaller footprint at higher operational efficiency. And we've used this technology for over 50 years. Here you can see the global manufacturing footprint across Covalis. We have facilities and teams across North America with manufacturing presence in Canada, the US, and Mexico, plus complementary capability through Relco. Okay, before going into the core mechanism, I'll do a quick ion exchange refresher so we are aligned on the fundamentals. Okay, let me frame ion exchange in plain terms. You have a liquid stream and the resin, and ions are reversibly swapped between them. The resin is a high surface area polymer with fixed charge functional groups, and those sites selectively hold certain ions from the solution, while other ions replace them to maintain the charge balance. Over time, the resin capacity gets used, so you typically apply a chemical regenerant to restore the resin and repeat the cycle. With the basics definitions covered, I want to connect the visual to the chemistry. On the left, you can see the actual resin beads. These are small spherical polymer particles. Under magnification, as shown in the middle, you can see how uniform and spherical they are. These beads are typically in the range of hundreds of microns in diameter. If we zoom in further to a single bead, as illustrated on the right, the structure is not solid plastic. It's a porous polymer network that internal surface provides the surface area where ion exchange happens. Okay, here we can see what's happening at a molecular level. The resin backbone contains fixed charge functional groups. In the cation exchanger, those sites are negatively charged and attract positive ions. In an ion exchanger, it's the opposite. The sites are positively charged and they attract negative ions. The counter ions are held electrostatically at these exchange sites. When the feed solution flows through, the target ions replace the original counter ions. That's the exchange step. And when we regenerate, we reverse the exchange and restore the capacity. So physically, we are looking at a small spherical polymer bead, but chemically, we are looking at a network of charge sites that selectively capture ions. Now that we are aligned on ion exchange basics, let's move to the core mechanism behind our approach, Recoflo short bed ion exchange. Recoflo originated at the University of Toronto in 1960s. On Recoflo, the resin bead is much smaller, on the order of about 20% of the diameter of a conventional ion exchange bead. When the bead is smaller, you get more surface area per unit volume, and the exchange sites are more accessible. That means ions don't need to diffuse as far into the bead, so the mass transfer is faster. In a conventional column, you typically have a tall resin bed, and the mass transfer zone is spread through the vessel. So the cycles can take hours, and you often run the bed very close to exhaustion to fully utilize the bed. With Recoflo, we use a compressed shallow bed, and we control the mass transfer zone as it moves. We stop the cycle before it reaches the bottom and then regenerate. This is what enables shorter cycles and high performance in a compact system. So what makes Recoflo different? The key difference between Recoflo and conventional resin is the surface area per unit resin volume, which is about 100 square meters per liter for Recoflo compared to about 25 square meters per liter for conventional resin. Practically, surface area per resin volume matters because it defines how many active sites are available to contact the liquid at any moment. With fine mesh resin and shallow compressed bed, the liquid at any moment can reach the active sites, and ions don't need to travel as far to reach the sites. At the same time, the void space between beads is reduced, which enables a more compact bed. That leads to a faster mass transfer, shorter cycle times, and sharp breakthrough profiles, which I will show you a bit later. In other words, chemistry is same. Recoflo changed the geometry, so it performs at high throughput with a much smaller footprint. With the key differences clear, let's translate them into practical operating features. Here are the key features. The short bed design reduces flow resistance. High flow rates allows shorter processing time, and efficient regeneration enables quicker cycles. Because the system is compact, it saves space and integrates easily into other processes. The result is a consistent performance with less product dilution. And here's how those features result in practical plant-level advantages. From a full-scale system perspective, the benefits are straightforward. A smaller footprint and less resin, which drive lower capital requirements through a smaller vessel and reduce installed complexity. Here you can see a conventional ion exchange softener we built and shipped to a customer. This was an early stage of production, and you can compare the vessel size to a typical Recoflo bed. On operating side, shorter cycles, less waste, and simpler operations reduce ongoing costs and burden. And in terms of performance, you get clean cutoffs that supports a stable product quality. The next question is where this platform is applied. Recoflo technology is applied across proven unit operations. For example, the acid purification unit, or APU, is used to remove dissolved metals from processed acid to maintain low contaminant level, commonly in areas like anodizing and refining. The salt separation unit, SSU, uses a specialized resin with a high affinity for chloride to separate salts and lower contaminant level in industrial operations. And DPU is a phosphoric acid recovery system that removes dissolved aluminum from phosphoric rinsed water and concentrates phosphoric acid for reuse. For aluminum finishing, our ANOPure is adopted specifically for sulfuric acid purification in anodizing, where dissolved aluminum is continuously removed to keep contaminants low. Our AMIPure applies Recoflo ion exchange to remove heat-stable salts, which are the source of corrosion and performance loss, from an amine circuit in refineries or the carbon capture sector. The purified amine then recycled back into the process. Ecotech also offers mobile AMIPure and amine purification service that connects to the existing amine circuits when purification is needed. The reason I'm showing this is simple. It demonstrates that the same Recoflo platform is engineered and applied across multiple industrial separations. Now I'll narrow it down to what matters for today, our core water purification capabilities. We have extensive experience in water purification, such as produced water and industrial DI. And to anchor that in real deployment, our first WDU was sold in 1991. So we have more than 35 years of experience with water purification. Water purification experience matters because you are dealing with the real-world variability, changing water chemistry, solids, and operating conditions, and the system still has to be reliable. We have a strong in-house ion exchange process design and system engineering. That means we don't just supply resin. We engineer the full solution: configuration, cycle strategy, regeneration approach, and execution. So for us, Recoflo systems are not lab exercise. It's a design and engineered unit operation built on real industrial experience. Okay, let's look at one of our water purification systems. This is a full-scale WDU we built and shipped to a customer. It's a small and modular and make it well suited for a scale-up with multiple trains. With the platform application covered, the next piece is how we de-risk performance through pilot capability and treatability studies. Here at Ecotech, we conduct in-house and on-site pilot treatability studies to confirm performance and optimize full-scale design, so we can reduce scale-up risk due to unknowns before committing to commercial equipment. For example, in DLE, brines differ site to site in feed total hardness, TDS, temperature, and impurity chemistry. So each project needs a tailored approach based on the actual feed. On this slide, you can see 3 pilot units for different applications. The first one is based on our SSU. The pilot in the middle is the WDU, and the third is the DLE pilot unit that we built and deployed to the field for an on-site trial. In that DLE pilot unit, softening was incorporated into the overall pilot system. And that work sits within our overall lithium track record. CaCO₃ has been involved in direct lithium extraction development. We developed LiPro for commercial applications within CaCo's lithium commercialization program, with performance proven by field trials. After the corporate transition, LiPro was retained by CaCo Industries, and CaCO₃ is now part of Covalent Separation Solutions. So, combined with our ion exchange experience in water purification, this DLE background leads directly to today's topic, Recoflo softener. Recoflo softener leverages our water purification experience with our history in the lithium market. It's validated across multiple brine and operating conditions, and it targets a compact footprint with improved efficiency and lower operating costs versus conventional softening. Now that the technology foundation is set, we can move into the details of our Recoflo softener. To place the softening correctly, I will first walk through the DLE flowsheet at a high level. Starting with the brine source, the first job is pretreatment, removing suspended solids and protecting everything downstream. CaCO₃ can support this with our spectrum filter unit operation, and covalent membrane solutions provide UF capability that has been applied in DLE flowsheets and demonstrated at large scale. Next is the core DLE step. That's where lithium is selectively captured and released, and we generate the eluate. After the core DLE step, the next focus is impurity removal, especially calcium and magnesium. This is exactly where the Recoflo softener is designed for hardness control in the DLE flowsheet. From there, the flowsheet moves into RO and conversion, and finally evaporation crystallization to reach technical grade lithium. We can support RO through covalent membrane solutions as well. One useful way to look at this flowsheet is to recognize several of these steps are concentration and finishing steps. RO and evaporation crystallization both move the system toward higher concentration. With the flowsheet context in mind, let's focus on why eluate hardness management is critical. As concentration increases, the system becomes less forgiving. Even a small hardness that slips through into downstream unit operations can trigger scale formation. Calcium and magnesium are classic examples. If they carry through, they can drive scaling and fouling, reduce purity level, increase operating costs, and create instability in conversion and crystallization. In practice, that shows up as pressure drop, loss of heat transfer, and more frequent cleaning. And it can become a bottleneck for RO, where scaling is a well-known limiting mechanism. That's why DLE flowsheets combine membrane steps with impurity control. The goal is a stable, predictable feed into RO, conversion, and evaporator crystallizer. So hardness removal is not a nice-to-have polish. It's a reliability control step that protects the rest of the flowsheet. With this in mind, let me introduce the Recoflo softener technology as an advanced softening solution for DLE. At its core, Recoflo softener is a patent-pending high-efficiency ion exchange softening process. It uses a short bed, high-flux resin configuration, which is why we can provide a compact footprint and shorter cycle time. It's also designed for flexible feed conditions. And importantly, it's meant to integrate into existing DLE operations without requiring a complete redesign of the plant. If you look at the schematic, the operation is straightforward. DLE eluate enters the unit, and the output is softened product stream. On the regeneration side, we use sodium chloride, and water for wash and regeneration generates a waste stream. The technology is built around high-efficiency short bed ion exchange, which can be understood easily, controlled clearly, and repeated cycle after cycle with stable output. The thinking behind this design is keep the process efficient, but also keep it practical for real plant operation and lower both CapEx and OpEx. Now we have introduced the technology, let's define the operating range and regeneration approach. The ideal feed range for Recoflo softener is temperature between 10 to 60 degrees C, the total hardness up to 3000 ppm, and TDS in the feed up to 20,000 ppm as calcium carbonate. We can do more beyond this range, but they are trade-offs. The key point is that we design around your feed characterization and your target spec, because these have an impact on the sizing and cycle strategy, and ultimately on the CapEx and OpEx. The system regenerates with standard sodium chloride brine, which is most DLE sites, that brine is often already available. So you avoid chemicals like sodium hydroxide and hydrochloric acid, which reduces both cost and environmental impact. It also targets short regeneration cycle time and reduce rinse volume. With the operation range set, we can move to the performance. On the performance, the hardness in the treated product is below 5 ppm as calcium carbonate. If the application requires an even tighter spec, with a small polishing unit, we can reach below 1 ppm. On lithium recovery, we have developed a targeted approach to minimize lithium loss during softening. Within the ideal feed range we just discussed on the previous slide, we maintain lithium loss below 3%. On utilities, water consumption is typically in the range of 1 to 50 to 1 to 20 water to process feed by volume. In some cases, that water consumption can be reduced further depending on the feed characteristics. These are the typical profiles for the product and regeneration step. The product profile represents their service run when we are treating the DLE eluate and producing softened product, and regeneration profile represent the regeneration step when we restore the resin capacity using the regenerant. Because the void space between beads is reduced and the bed is compact, we see sharp breakthrough behavior in both product and regeneration step. The cutoffs are clean and efficient, which reduce the chance of contamination. In day-to-day operation, sharp profiles means the switch points are predictable and you can stop the service run at a clean cutoff. Regeneration efficiency and return the service without dragging a long tail of mix quality. That reduces the need for complex lead lag configuration, minimizes off-spec handling, and make it easier to integrate into an automated DLE where you care about a stable downstream performance. Now let's translate performance into economics, starting with CapEx drivers. On CapEx, the reduction is driven by three things: less resin, smaller vessel, and a smaller footprint. A smaller footprint also translates directly into less piping, wiring, and structural steel, which reduces total installed cost. In an example case, we see 30 to 50% CapEx reduction versus conventional softening. As always, this is case specific. It depends on your flow rate, feed composition, target spec, and redundancy philosophy. With CapEx covered, let's take a look at deployment. From a deployment standpoint, the system is compact, modular, and skid mounted, factory assembled, pre-packed, pre-piped, and pre-wired and tested, which requires minimal on-site assembly and supports faster commissioning. What matters next is the OpEx drivers. On OpEx, the key drivers are lower regenerant cost, reduced water and energy use, shorter cycles with less downtime, extended resin life, and lower waste disposal. We also avoid chemical usage, which simplifies handling and reduces operating burden. Here are two examples of consumption and cost cases. In these two cases, all chemical requirements are normalized per 1,000 US gallons of product. And in both cases, the conventional softener approach relies on acid and caustic, while for the Recoflo softener, only sodium chloride is required. In case 1, the conventional system uses 85 US gallons of hydrochloric acid and 30 US gallons of sodium hydroxide. And it requires 130 US gallons of water to wash the bed before the next cycle. In contrast, Recoflo uses 60 US gallons of sodium chloride with only 20 US gallons of water. The annual chemical consumption cost shown is about $1.5 million per year for conventional versus about $400,000 per year for Recoflo softener. Keep in mind that using sodium chloride brine, which is often already available on site at no extra cost, simplifies the logistics and reduces the number of chemical interfaces in the plant as well. In case 2, the conventional system uses 310 US gallons of hydrochloric acid and 120 US gallons of sodium hydroxide with 500 US gallons of water. Recoflo uses 315 US gallons of sodium chloride with only 100 US gallons of water. The annual chemical consumption cost it's shown is about $4.8 million per year for conventional versus about $1 million per year for Recoflo. These are example cases, but they show how regeneration chemistry and water consumption can materially impact operating costs. The benefit is not only one chemical is cheaper than other, but also that the operating approach becomes simpler. Fewer chemicals, less wash water, and fewer handling steps usually means less routine burden on the plants. Over time, that kind of simplicity can be very valuable because it supports both lower cost and a smoother day-to-day operation. For many operators, that simplicity is as valuable as the cost reduction. With those example cases, let me bring the value proposition together on the next slide. From a capital perspective, the main drivers are straightforward. We use significantly less resin and we can reduce vessel size. Depending on your project specification, the system scales by adding modular parallel trains while still maintaining a much smaller footprint than conventional softening, which also reduces the amount of piping, wiring, and structural steel. In the example basis we've shown, that translates to about 30 to 50% lower capex and supports lower TIC. From the operation standpoint, this is designed to be easier to live with. Regeneration is simpler with only sodium chloride, no acid, no caustic needed. Cycles are shorter and you use less water and energy. Over time, that also means longer resin life and less waste, so the operating burden and the cost both drops. From the execution standpoint, the system is designed for speed. It's modular and skid mounted, factory tested, and it requires minimal on-site work, so commissioning can be much faster. And finally, on performance and reliability, we see sharp product and regeneration breakthrough profiles with clean cutoffs, robust operation across a wide feed range, and no lead type requirements. Now let's make it DLE specific, what this means for performance and integration in a DLE flowsheet. In DLE, one of the biggest operational challenges is variable eluate quality and hardness breakthrough, because they turn into a scaling, fouling, and unstable downstream performance. Recoflo software is built to take that risk off the table. It delivers low hardness product, keep lithium loss minimal, and regenerate using readily available sodium chloride with no need for hazardous chemicals. And it's designed to integrate into existing DLE operations, helping reduce cost and environmental impact. Okay, I guess with this, we've come to the end of our presentation. Thank you so much for listening. And now we'll take a look at your questions. We'll try to answer as many of your questions as time allows us. If anything needs a deeper discussion or site-specific review, we'll be happy to follow up after the webinar. Also, marketing team will be contact with you after the webinar and sending an email with a recording of this webinar. Thank you. Okay.
So Madi, our first question is with respect to resin life. What is the typical resin life for the DLE applications for your softener from Kinley Moore?
Okay, that's a very good question. For our Recoflo softener, because we don't use the chemicals and the cycles are shorter, the resin life is up to 5 to 7 years, depending on the temperature. So we are looking at 5 years minimum of resin life.
Any other questions from the field? Nothing yet. I guess along the same line, it's worth noting that in these DLE type applications, there's nothing really that's going to oxidize our resin or otherwise foul it. So we do expect really long life, and it's fairly clean because we're going to see DLE eluate after some other core processing steps like solids removal and the core DLE step, that lithium selective step. So we're going to see very clean brine. We don't expect there to be anything that's going to oxidize or foul our resin like iron or something. So really long life type of application.
I see a second question there, Louis.
I don't see it yet. Oh, here we go. Okay. Share the presentation. Yes, so the presentation will be made available. This recording will be made available to all people who've registered. Has any commercial unit been deployed? So we have not deployed this style of softener in a lithium application, but it has been deployed in produced water treatment for softening water that is co-produced with oil in heavy oil fields like what you'd find in Bakersfield area in California. We are, however, looking forward to participating in pilot tests in the field or doing treatability studies in-house with solution which may come from a site. We're very happy to work with people in that way. Next one, what is the typical delivery time of a skid after receipt of PO? So I think, I mean, these are fairly large scale projects. I think if you're talking a commercial scale application, which may be, 10, 12 large scale skids, I would say we could probably deliver a complete system, 12, 16 months after award of a contract, something in that line. That would probably be a staggered delivery on a commercial scale. And if you're talking about maybe a small scale pilot to participate in a demo plant, significantly less. I think we could probably get something out in 30-ish weeks, going through all the design and fabrication steps. If it's a very small pilot, obviously much quicker. Can you also include, oh, wait, let me get back here. Okay, can you please explain lithium loss of less than 3%?
Okay, that's a very good question. For lithium loss, we are calculating that percentage around our softener. So it means that during the service run, we have some of the lithium goes into the resin. And if we cannot remove them during the on stream, sending back to the eluate or another method that we have, they all go to the waste when we do regeneration. So we have a very sophisticated and a very novel approach that we have an extra step that will remove those lithium from the resin before going to the regeneration. So that's why we can keep the lithium loss less than 3%.
Okay, someone has asked for contact information. So I'm just going to copy my contact info into the chat, or into the Q&A rather. Do you provide this globally or only in North America? So CaCO₃ supplies equipment globally. So yes, we can design and build to international standards and standards specific to certain territories, certain countries. So yes, short answer is yes to global. Can we buy only the resin and build a skid? So no, we would not typically engage in a project of just supplying resin and detailed design information. That would be giving away a lot of IP. So I would say, I mean, maybe we can probably have a discussion on this. Again, my information is in the chat. Please send an inquiry to me. I would say generally the answer would be no, but please reach out and we can have a more detailed discussion. Second part of that question, do you have different types of resins? So CaCO₃ has many types of ion exchange resin-based processes for chemical recovery or for chemical purification or water treatment. So we have many resins. The softening, DLE eluate softening is really one main kind of resin for hardness removal for that divalent. Next question, can you design for 30 bar operating pressure? So I'm going to say yes. So we have a very capable mechanical design team, and while I would say most of our equipment is rated for 10 bar, we can certainly design for higher pressure applications. And thinking back to the work we did in produced water, which I referred to earlier, we definitely have done designs which far exceeded that, the 10 bar. We're probably exceeded 30 bar. So again, yes to that. Range of power demand. Oh, tough question there, because that's going to depend on the type of feed we're dealing with, volume of feed, etc. Madi, is that a question that you could address in terms of per 1,000 gallons or some basis? I don't think so. I think it's too broad of a question.
Yes.
Yeah.
It may be better, Louis, in that case to take that offline and talk to who's interested with some sort of sizing or design basis. Then we could certainly provide that.
Yes. Yeah. Let me just I'll cut. So for John, who asked about power demand, I put my contact info as a response to your question. Please reach out and we can look at it. We're going to need a bit more detailed information. Kevin Williams, in your example, you used 1,000 gallons of water for 1,000 gallon of product, yet the performance ratios were 1:20 and 1:50. Usage seems higher. So I'm not sure. Madi?
Yes. So those are the example kits that we provide, and it depends. Yes, you're right. The ratio is not between the number that I gave you, but it depends. And it can even be lower than that or higher than that based on the feed characterization. So it's not a single number that we can point out, and it depends on your requirement. So if you need some numbers that match your requirement, we can talk after the webinar with some details about what will be the requirement based on your application.
Next question is about nitrogen. Do you need any nitrogen for purging or utility?
No, we don't use any nitrogen or purging for utility. We normally use air for the actuators, and that's it.
Good question so far. It's always nice to see good questions. People are paying attention, and obviously I think the material resonated. So it's nice to see. Now, another question. Do you have a range for skid weight? One run, one leg, one wash. Do you need concrete pad? Do you need overhead crane? Okay, so firstly, and this brings up a really good point for Nidam Abed. Great question. So firstly, the way our system runs, we don't rely on any kind of lead lag type of process. So it's just one stage. We can have multiple skids for high volume flow rate, but it's only one stage. We will have multiple trains, one stage. So that simplifies piping significantly and installation. A skid, I think in Madi's presentation, there was a rendering of a typical skid. So a large scale complete skid would probably weigh a few tons because it is all welded steel base. Our bed is also heavy, thick welded steel with flat top and bottom plates and a bed spool that's all welded steel with a lining. So yeah, you're looking at a few tons at least for each single skid. Yes, you would need some form of concrete pad. This, of course, is at commercial scale. If you're talking about a smaller unit for demonstration or piloting, that'd be considerably different. I hope that addresses your question. And you also said do you need overhead crane? So for maintenance purposes, you are going to need some kind of lifting device to remove the head plate off of the ion exchange bed for replacing resin, replacing screens and gaskets and things like that. We do expect our resin to last 5 years or more, so that's not going to be a frequent occurrence, but you will need lifting equipment for that. Hope that addresses your question. What platform do you use for control and instrumentation? Okay, so in terms of like hardware, software in our control cabinets, we're somewhat agnostic. We can build and design to match site requirements. I think we standardize for our own purposes around Allen Bradley, as far as I know, and Ashwin or Mahdi, if you have a different response, please let me.
Yes, that's the one. Yep.
Yeah. Where is the resin made, produced? Okay, so our resin, we do not disclose a lot of details about our resin. So I can't address that question. I will say that our resin is made by a third party to Ecotech specifications. So these are specially made batches of resins for Ecotech that are then QC'd in-house. Each batch is QC'd. And that's about all we'll disclose on that. And then we have a lot of questions. This is great. Nadam, again, thanks. We'll discuss further in coming days. Great, Nadam. So I've posted my contact information into one of your questions. So hopefully you've picked that up. Reach out to us. We'll be happy to have more detailed discussions.
And we have a question from Kevin.
Yes. Okay. Well, let me read that out for everyone. The units are fabricated of carbon steel, but internally lined. Any issues with corrosion due to high salts and chlorides? No issues with liner integrity. Okay, so I would say generally no. Good question. So the spool piece, the centerpiece of our resin bed, is generally done as carbon steel with a rubber liner. We've got a lot of experience with that particular configuration, and no, we do not consider that let's say a high risk.
Yeah, and also for the pipes and everything, because it's mostly highly, chloride concentration. So we do the piping and everything lined.
Right. Wait a couple of minutes for any other questions. We are at time right now, so it is 1 hour. I think maybe we can give it another minute and then maybe close this out. Great questions, everyone. Thanks for your interest. And your participation. It's really nice to see people asking intelligent, thoughtful questions. And thanks, Mahdi. That was a great presentation.
Thank you.
And all your hard work, Mahdi's. Another question. Are PDH certificates available for this session? I could not answer. I don't know. I don't believe so. I guess that's some form of like continuing education or something. Anybody understand the question better than myself?
No.
Okay. Professional development, something, I assume. I'm going to say probably not, but maybe we'll take that question away and see if we can address it with Kinley. Zu, thanks you. Thanks a ton. And thanks, Arazu, thank you for attending. Appreciate it. Okay, maybe we can close it out now. All right, thanks everyone for attending. Really appreciate your participation. Okay, and someone just commented that PDH is for PEO reporting. So that's something interesting to take away and respond to the crowd. Okay, thank you. Thank you, Nadam, for that clarification. I think we'll close out the presentation now. Again, thanks everyone for attending. Thanks, Mahdi. I know you worked really hard on putting the presentation together and all the work that went into developing the softening process. So thanks for your hard work.
Yes. Thank you so much. And the team was, really working really hard to get it done. And thank you.
All right, everyone. Thank you.
Okay, thank you. Have a good one.